Hello and welcome back to our next example on our series of graphing rational functions and generating algebraic forms from their graphs. In this example, we are going to examine the graph on the left, and this will have an oblique asymptote, and we are going to step through our process in order to determine the algebraic form of this particular graph. So when we look at this graph, we see that we have two vertical asymptotes, and this time we have an oblique asymptote at the line y equal x minus 1. We see that we have a root at -3, a root at 1, and a root at +4. We have a y-intercept at 0, -6. So now we're going to begin our analysis. We're going to use our tools and our definitions and our ideas to generate an algebraic form for this graph. So we begin with identifying the domain. In this case, the domain is going to be all of the values except for -1 and 2. So when we examine our graph, we see that the graph is going to approach either positive or negative infinity when I am close to x equal -1 or close to x equal 2. This implies that 2 and -1 are not in the domain because they're not paired up with a finite real number. They go off to infinity. And more importantly, this implies that x equal -1 and x equal 2 are, in fact, vertical asymptotes by definition. So we have vertical asymptotes at x equal -1 and x equal 2. There is a sign change around these vertical asymptotes. Around the vertical asymptotes, it's positive on one side, it's negative on the other side. Now remember that vertical asymptotes correspond to roots of the denominator. So we have roots of the denominator at -1 and 2. That means that x plus 1 and x minus 2 are factors in the denominator. And because there is a sign change around these vertical asymptotes, we know that the multiplicity of these roots has to be an odd number. So we're going to set that to be 1 for now. We'll adjust it if we need to later. So using all this information, we have a rational function, r of x is equal to n of x, some polynomial to be determined right now for our numerator, divided by the product of the factors x plus 1 and x minus 2. There is an oblique asymptote at the line y equal x minus 1, and this implies the degree of the numerator is greater than the degree of the denominator. Because the oblique asymptote is linear, it also implies the difference in the degrees is 1. So the degree of the top, or the numerator polynomial, will be 1 bigger than the degree of the denominator polynomial. We have x-intercepts located at -3, 0, at 1, 0, and 4, 0. The graph crosses the x-axis at each of these points. So remember, x-intercepts correspond to solutions to the numerator. So we have a root at -3. That means x plus 3 is a factor. We have a root at 1, and that means that x minus 1 is also a factor. We have a root 4, which means x minus 4 is also a factor of the numerator. And because there are sign changes around each of these roots, this means that each of these factors has an odd multiplicity. So we're going to set that to be 1 for now. We'll adjust it if we need to. Our last piece of information from the graph is that we have a y-intercept at 0, -6. And we'll use that to get our leading coefficient. So right now we have a rational function that's going to be equal to some value, capital A, that we'll determine in just a minute, times the product of the factors, x minus 1 times x plus 3 times x minus 4. That's all going to be divided by the product of the factors, x minus 2 times x plus 1. Now we're going to use the y-intercept to determine that value of a. We know that when I put 0 in, I get -6 back. So when I plug 0 in for x into my template for my rational function that I just generated, I end up getting 12 is equal to 12a, and this means that a has to be 1. So our rational function has the form x plus 3 times x minus 1 times x minus 4 divided by x minus 2 times x plus 1. So, and if you notice, we do have the degree of the numerator 1 bigger than the degree of the denominator. That means we have an oblique asymptote, or as it's sometimes called, a slanted asymptote. And this also satisfies all the other conditions set forth by the graph. So this is the algebraic form of our rational function represented with our graph on the left. And I thank you for your time and attention.